Okay, so the point of the problem we're about to do is to find the equation of a tangent line, right? So you might come back a few days from now when you have to find the equation of a tangent line. You go, wait, how did we do that? And you come back, check out the video. But also we're going to find the derivative using the definition. That's a thing you have to do from time to time. So you might come back and check on that as well. And then we'll have to do some algebra along the way in order to get our line. So let's jump into it. So here we have a function graphed. So f of x is equal to x squared minus x plus 1. We know that that's a quadratic function, and we see it right here. Well, let's say I wanted to find the equation of the tangent line at x equals 2. Okay, so that's my goal. Find the equation of the tangent line when x equals 2. Well, we can see in our graph, and we're going to need these values, the point on that graph at x equals 2 is 2, 3. Right? So we're going to need both of those values later in our calculation. So first, you want to identify what that point is for the tangent line we're being asked about. And I said at x equals 2, so you go, okay, well, when x equals 2, you figure out the point. We've got our point there. Okay. Now what we have to do is jump over to doing a bunch of algebra. Okay, so here we have the function that we're dealing with. Now, in this case, I'm using the definition of the derivative to find the derivative. Later on, we're going to learn shortcuts for the derivative, which are going to make things a lot easier. But in the beginning, we have to find our derivatives using that definition. So that's the limit of the difference quotient. Remember, your difference quotient is just a slope formula. We'll look at that in just a second. And in that difference quotient, we're going to need to calculate f of x plus h. Okay, so we're going to go through and calculate that. What you want to remember is that when you square a binomial, you don't just end up with the square of the terms in the binomial. In other words, remember that when we take f of x plus h, what we do in this function is everywhere there's an x written up here, we're going to put x plus h in there. And there's a tendency I see people when they do the squaring part for x plus h is they make it x squared plus h squared. That's not how you square things. X plus h quantity squared, you got to go through and do your polynomial multiplication. You got to do your FOIL, right? So that's how you end up with the 2xh that gets in there. So just remember that if these aren't coming out right, that may be the issue. I see that frequently. So when we take x plus h and we plug it into f of x and we multiply everything out, we get x squared plus 2xh plus h squared minus x minus h plus 1. That's all the f of x plus h piece. Okay, so then what we want to do is we're going to take those values and we're going to plug them into our difference quotient. So remember, we've got the limit of the difference quotient. That's what the derivative is. It's the limit of the difference quotient. And what is the difference quotient? Well, it's this thing right here, but notice it's just slope. That's all it is. It's a fancy form of slope. In fact, some calculus books use a different formulation of this that looks even more like slope. But this is kind of the way most modern books write it. It's a little more convenient in many circumstances. But if you think about it, what do we have on top? We have two function values. What are function values? They're just y values, right? And what is this h on the bottom? If you think about it, that h is actually the distance between our x values. So what do we have on top? We have a difference in our y values. On bottom, we have a difference in our x values. It's just the slope. And that's exactly why we're using the derivative in this case, is to find the slope of the tangent line. That's the whole reason we're doing this. So it actually makes a ton of sense, right? Everything looks good. So now what we're going to do is take that limit of the difference quotient and we're going to plug in the values for our particular problem. We've already figured out the numerator because we've got our f of x, that we had to do that to get started with the problem. We've calculated the f of x plus h, and I've now put them into the difference quotient. Now here's another place to be careful because I see mistakes get made here. People will write this is the minus f of x plus piece out here. If you don't put the parentheses in there, people only apply the negative to the first term in that function. So I put these parentheses here so we can remember, oh, that negative has to get distributed inside. It has to apply to all of these terms. Otherwise, things aren't going to cancel right, and your problem's just going to be a disaster. So that's our next step, is we're actually going to go through and we're going to distribute that negative in. Okay, so we get essentially the same thing, except now that negative has been distributed in, and we get this. Now at this point, it's starting to look like kind of a mess, right? You go, man, this is getting really confusing, and we haven't even done a very complicated function. It can get really confusing when we start having square roots in there, rational functions, all of these. Your algebra has to be pretty strong in order to get through these. This is actually not bad. But one thing that's going to you want to recognize is usually in these problems, right about the point where you start getting overwhelmed, like right here where you're like, that numerator looks crazy, right? That's usually about the point where you're going to have a bunch of things canceling each other. Now, if we did this right, the terms in our minus f of x piece should cancel with terms from previous part of the numerator here. So notice we have a negative x squared here, and we have a plus x squared. We have a plus x and a negative x. We have a negative 1 and a plus 1. So all of those are going to cancel out. If that happens, then you're on the right track, okay? If all of a sudden some terms aren't canceling, then you made a mistake somewhere previous. Either when you were distributing the negative, you didn't do that right, or up here when you did the f of x plus h piece, you didn't do that right. Something went wrong, because this canceling we're now getting is not just, a happy accident. It's how it works, right? It's kind of how things come about. So when we simplify all that down, we get the limit as h goes to 0 of 2xh plus h squared minus h over h. Now we need to be careful here. There's a little bit of a subtlety. So notice what's going to happen is we're going to go through and we're going to divide everything by h. And there's a nuance here that gets missed frequently, and then there's just a common mistake people make right here. So the nuance is we have to be careful, because you go, wait a minute, if my h's are going to 0 and I divide the top and bottom by h in order to simplify, then aren't I in effect dividing by 0? And that's not allowed in mathematics, right? You have to be careful. That's one of the ways we've defined the limit. The limit, remember when we looked at our limits, we don't care in the limit what's actually happening at h equals 0, like right at the point. The limit is concerned about the points that are near the value that we're concerned about. So we can say h is non-zero. It's some non-zero number. There's some small non-zero distance. It's tiny, 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 minuscule, but some non-zero distance between the 2 points that we're concerned about. We're shrinking that h down towards 0, but it's in effect non-zero. Okay, so if we go ahead and divide the top and bottom by h, we're going to get an h to cancel. Now be careful. I see a lot of times in a problem like this, people will cross this h out and they'll cross this h out and go, oh, good, those two things canceled out. That's not canceling. That's just wishful thinking. That's just drawing lines through things that you don't want to be there. In order to cancel, you're actually dividing. If we divide the top and bottom by h, the entire numerator has to get divided by h. Okay, so when we go through and do that, we will see that we're now getting into something much simpler. So we get the limit as h goes to 0 of 2x plus h minus 1. So this is just what you get when we take that step before and we've divided an h out. And now we're actually going to perform the limit. So it's really important when you're writing these, and sometimes people miss points for doing this. But it's important because mathematical notation, right? If you do it wrong, it's not just that you wrote the wrong symbol, it's that what you're doing is actually incorrect. You're making a mathematical statement that isn't right. So you need to be really careful and make sure that when you haven't taken the limit yet, that you're still writing the limit. See how I keep writing the limit here each time? Right? Because we haven't taken the limit yet. But now we're about to take the limit. So once we take the limit, you shouldn't write limit anymore. Right? It's just an operation. That would be like squaring something and then you leave the squaring symbol up there. We don't do that. If you take 3 squared, once you make it 9, the square isn't up there anymore, right? The exponent goes away because you squared 3. It's the same thing here. Once we take the limit, we stop writing limit. That's why you can see over here now, there's no limit anymore, right? We've taken the limit, so now we just have the function. So what happened is we took this h and we shrunk it down towards 0. So this term was shrinking down towards 0. It's infinitesimally small. So in the limit, when we shrink that thing down ridiculously small, it becomes the function 2x minus 1. Okay, so that means we've done the hard part of the derivative. So we can now figure out what we're getting here. So that we can formally write the derivative of f is equal to 2x minus 1. So now we have our function, and we're actually most concerned about a specific point. We went through and found the derivative. We could calculate the derivative at any point we want, but we specifically want it when x was equal to 2. Remember back to our picture? The whole question is we wanted to find the tangent line when x was equal to 2. So we're going to take our derivative and evaluate it at 2. That's going to tell us the slope of our line, of our curve, our original curve, the rate of change of that curve at x equals 2, and it turns out the value is 3. So for us, what that means is the slope of that tangent line we're about to find is 3. Okay, so how do we finish this problem off? Well, we're looking for the slope of a tangent line, and a tangent line is a line. Therefore, we can write it in the form y equals mx plus b, and we just saw from the previous problem, we calculated that the slope we care about is 3, so let's go ahead and plug that value in, right? And that's half the problem, right? Finding the slope of a line, then we have to find the intercept. So we've already got the slope. We had to use calculus to find that slope, but from here on out, it's algebra. So we've got y equals 3x plus b. Okay, so how do we solve for b? Normally in an algebra class, the way you would solve for b is that you would now take the values from a point and you would plug them into this equation. Well, where are we going to get values from the point? Well, remember, we looked at that at the very beginning of the problem. So if we go back and remind ourselves what this looks like, remember, we figured out the point on our line was 2, 3, right? Because originally the problem was stated. I stated it in a way that we wanted the tangent line when x was equal to 2. So we look at x equals 2. We figured out the y value was 3. So, oh, that's the point we should use then. You go, wait a minute. Why are you using a point from the curve to be a point on the line? Because this point is going to have the tangent line going right through it. This point is shared by the line and the curve. That's what's so important about it, is it's on both of those things. Okay, so now knowing that we're going to use the point 2, 3, let's go back to our algebra. So we've got y equals 3x plus b. So now we want to solve for b. So we're going to use that information, the point that we just saw that's on the curve, that's also going to be on our tangent line, right? They have that in common. So we're going to use the point 2, 3. Now we just plug those in, just like we would do for any find the equation of the line problem, where you've got the slope already figured out and you've got a point. Now you just plug those values in. So we can see that we're going to get 3 equals 3 times 2 plus b. And then we're going to go ahead and solve for b. We'll get that b equals -3. And then we just have to go back and plug that into the equation that we had up above. And we end up with y equals 3x minus 3. Now, going through and like you can see, it took quite a bit of work in order to find the equation of this tangent line, but checking it is super easy. All you have to do is graph, and your brain is going to immediately tell whether it's correct or incorrect. So if we go back to our original equation and we graph that line, y equals 3x minus 3, yeah, that's what a tangent line is supposed to look like. So it's going through that point. We can see that point being shared by both the curve and the tangent line. We can see that tangent line coming in, doesn't really cross our graph. It just comes in, barely touches it at one point, and then goes through, continues that behavior. So it looks like it's supposed to. So we know that what we did is correct. In fact, what I'll say is when I was setting up this problem, I made a mistake in my algebra, and I had this. Except when you go to graph this, you can immediately tell that's not right. That's not right at all. Like, so many things are wrong about this tangent line. It's not going through the correct point. It's not a tangent line, right? It's cutting through the graph, even though it's not just coming in smoothly and touching it. It's not approximating at the graph at any place, right? So nothing about this line looks right. And then I went through, I found my mistake, and then now you know, oh yeah, it's totally right now, because that's exactly what a tangent line is supposed to look like. Okay, so that's how you go through, that's how you take the derivative using the definition, and that's how you find the equation of a tangent line.